Well, I'm Gert-Jan Slokker, coming from the TU Eindhoven. I'm going to present my masterwork, my master thesis. And indeed, you already pronounced what I did, but it's quite a long sentence. But I performed an automatic local identification of complex nanoscale plastic deformation mechanics in a polycrystalline zinc HV microstructure. I especially want to thank my supervisor, Johan Hoefnagels, sitting there, for inviting me into this conference. Well, I think that everyone knows that steel is prone to corrosion, as corrosion will actually deteriorate your steel properties. And in order to prevent that, typically people put a coating on top of their steel. And an example of that is zinc coating. And they put it on the steel by using hot dip galvanized zinc process, in which you typically get a layer of around 10 microns. Well, and the zinc coating typically shows some, some pure ductility properties causing this micro cracking. And of course, that's not really beneficial for your protective layer. And that's actually also the main reason for my topic. We want to have a better understanding of what's really happening on the nanoscale. So if we know that, then we can really improve maybe this coating by adding all kinds of ingredients. And then we can really reduce this pure ductility property. The latest point is here. And we can actually reduce the amount of damage. Well, what kind of plastic deformation mechanics could we have in zinc? We could have intergranular crystallographic slip. In case of zinc, we could have 30 potential slip systems coming from 5 different families, which we can describe by a certain plane and direction. And within single crystals, we actually know that basal is dominating. We could also have deformation twinning. For zinc, we have one family, which gives actually 6 different twinning systems, and they actually can be described by a certain plane and direction, again, identical to a slip system. We could have intergranular grain boundary sliding and/or opening, or we could have grain boundary migration. And one of the question I now have is, how can we really identify these different deformation mechanics, and preferably automatic, because it opens the world for statistical analysis. Well, before we can analyze data, we have to really measure some data. So we perform an experimental cycle in which we first do some undeformed EBSD of a region of interest, and after which we put some really small particles on top of our sample surface, indium tin particles of around 90 nanometers, which we are going to follow into an in situ uniaxial tensile test. And well, you can now follow the different particles, getting your displacement field out by DIC, and then based on this displacement field, you can actually determine your strain field. And what we then do, we align the different data sets so that we have the required information on every pixel, and then we can continue to the analysis. To put it somewhat more visually, I have here the SAM images with the indium tin particles on top of it, and then well, by DIC we get the strain field. This is actually my loading cycles I use up to a global strain of around 6%. On hopefully the video works now. Yeah. And what you now can clearly see is that the strain is popping up. Now, specifically, you see some discrete slip, you see some diffuse deformations, and you also see some grain boundary deformations. And now, of course, we want to really know what's happening there. Well, can we already do something visually? Well, yes. So we have the strain field, we have our EBSD. So we know our crystallographic orientation, and we can actually project our slip traces, or we can actually project this plane into this plane, and that's doing by slip traces. And then you would say, okay, one of those could be active, but then you see already the problem. We have actually one of those 5 active, and we cannot really distinguish which of those 5. And the problem is that we do not really add everything. So we only added the plane information, but not really the directional information. So what we really need is a kinematic-based identification method. Well, there are some state-of-the-art methods like the RDR methods and the heaviside DIC methods, which are quite good methods, but also show some difficulties when slip traces are close together. Well, with our group, and I think Johan already introduced it, we have a quite funny name for an algorithm called SLIP system-based local identification of plasticity. And how does it now works? But this one really includes all the information. So here we have our undeformed EBSD. So we have a certain HCP structure with a certain plane, or slip plane, which has a certain normal and direction. Now we can actually calculate this dyadic product, giving this theoretical displacement gradient tensor, which actually gives us 9 components here. Well, we do our experiment, and we have our in-plane displacement field, and based on that, we can actually formulate our experimental displacement gradient tensor, giving these 4 components there, because we only have in-plane information. So then we also have to scrap the components there, and then in front of that, we put the slip activity, which actually says something about the magnitude of slip. Well, as said, in our case of zinc, we do not have one slip system, but we have multiple slip systems, in total 30, so we put the summation sign in front of that. And what we now can calculate is the residual, and if the residual is low, we say we have a positive identification. Well, my first example coming from a paper of Tijmen, which developed this method, he showed here an FCZ grain with some discrete slip in it. And actually, if you perform the slip method, it has been identified as slip system 1 and 80. But I wanted to closely look to this region of interest here, because if you see this pink region here, it has been identified as slip system 1 and 8, so 2 slip systems, but the strain band is not aligned at all with the slip trace. So if you would use conventional slip trace analysis, it would actually not pop out as this. So what's happening here is cross slip. Well, so the slip method works for diffuse and multi-slip in FCC and BCC, but now the problems occur that zinc is an HCP crystal, which is much more complex because you have much more linear dependent slip systems. So actually I came up with a different method called the plus slip method, which has some improvement with regard to the general slip method. Well, the first improvement we did is actually the radon-based pre-selection of slip system, which actually already pre-select of the 30 slip systems, which could be potentially active. So this is an artificial strain field generated based on the slip systems here. And what we now can do, we can perform the radon transform, giving this, which actually transforms the Cartesian coordinates in polar coordinates. And what we now get out is a sinogram. On the x-axis, you have the angle, and on the y-axis, you have this distance. And this intensity peaks are now corresponding to the angles here. So we can actually trace back which one they are. So we can actually really make a pre-selection of the ones which can potentially be active. What is a virtual case, but now an experimental case, for instance, this one. So for this grain, we already pre-selected 6 slip systems. And for this somewhat more complex case, in which you have crossing strain bands, we have pre-selected 7 slip systems. An additional improvement is that we added a degree of freedom, additional degree of freedom, the rotation. This really improves the output of the slip method. And there are some additional improvements which I will not discuss due to time constraints. Well, then the first example is this one. So we have already measured the EBSD pattern. We have pre-selected 6 slip systems. And now this plus slip output looks like this. So a lot of empty maps because we have pre-selected the 6 which are potentially active. So if we now only zoom in on this 6, well, this plus slip method now, it has been, the strain bands has been identified as basal 2 and 3. Well, the interesting thing is that this basal 2 and 3 are not showing really the high Schmidt factor, because basal 1 has the high Schmidt factor. So the grain rotation has some low contribution, so there's probably no grain rotation going on, and the residual is low, which means we have a positive identification. Well, now the somewhat more compact case, in which we have pre-selected 70 slip systems coming from 4 different families. And now we run the plus slip method, and now you only see the pre-selected ones. And now you would say, okay, pyramidal 1 CA is active in pyramidal 2. But we have to be somewhat more precise because the pyramidal 1 CA is quite identical in plane with regard to pyramidal 1 CA 2 and pyramidal 2 4, because we only have the in-plane information. So that's a pity of this method. So we call them non-conclusive or non-discriminatory groups, and we have to add up the slip activity, or we actually add it up. Well, the grain rotation in this case is sufficient. So if you would not apply this degree of freedom, well, the identification will not be that good as we saw here. And the residual is low, which means again we have a positive identification. So to conclude, we have successfully identified intersecting slip traces, but there are some limitations still due to the 2D measurement. Well, then the statistical results. So we performed the plus slip method on around 260 grains. Well, and then it looks like this. Well, you see again, basal was dominating, but we also have some non-basal activities. And if you look to the Schmidt factor distribution, then you see that the non-basal activity logically has been activated for high Schmidt factors, while the basal is quite ranging around almost 0 until 0.5, with the logical dominance for higher Schmidt factors. Well, then twinning, we also saw some twinning occurring. Here we have an undeformed EBSD, which already has a twin needle here and there. And if you look to the in-situ SE images, incrementally, you can clearly see this twin needles growing. And especially if you look to the strain field, you see this diffuse band growing, this constant diffuse band. And of course, now we also want to identify these twins, and the method we use for that, we call not slip now, but LITS, which actually is staying for local identification twinning systems. So for the twinning, well, as said, for zinc, we have one twin family, which actually gives 6 different twinning systems, and they can also be described by a certain planar direction. So we can actually now reuse the slip algorithm to calculate which twinning system is active. The only thing we have to change is that it should be, slip could be bidirectional and twinning is only one directional. So we apply a positive constraint. What we can also calculate analytically is the goniometric relations of the gauge here, which has been performed here. So we know that the output of LITS, like the twinning activity, not slip activity, should be around this value, which is an additional validation. And if you now look to these results here, so we have the first increment with the 2 needles here. Yeah, you see them already slightly popping up there. So this is the output of lids. And of course, no theoretical shear. So this value here should be almost identical to this theoretical value we have been already calculated. But especially for the second increment, you can clearly see that we have now identified this needle as this one, or this twin system, while this needle has been identified as that system. And as said, we have now the additional validation by using this gain shear. But what we also use is post-mortem EBSD, in which we really identified that these were the correct twins. Well, then grain boundary sliding. The method to identify grain boundary sliding we call LIBS, local identification boundary sliding. Within an anisotropic HCP lattice structure, grain boundary sliding could occur, and people say it's the movement of disconnections on the grain boundary or slip resistance deformation of the grain boundary. Okay. Well, we have our framework, and to wrap it a little bit up, we can actually describe a grain boundary by a sort of segment by normal and tangential. And what this method now again does is calculating a displacement gradient tensor. And now this grain boundary is moving, and what this LIBS method now can determine is actually this vector and a certain magnitude, of course, of the vector. And what we calculate is now the angle between this directional vector and this tangential direction. And we actually say if it is like a really low angle moving like this, it is sliding, or is it more like this? We say it's apparent opening. So let's look to a region of interest, like this green part here. So we have our strain fields, we have our smoothness grain boundary, and then we can actually determine the normal and the tangential. Well, the output of LIBS is looking like this. And then we determine the size of this vectors, which looks like this. But we know that the grain boundary sliding is a discrete event, so we have to integrate among these lines so that we get this line data. So we get really a line on this with the real sliding displacement in nanometers. Well, this opens the world again for statistical analysis. So we can now, for this complete map, determine this displacement. And then according to our threshold, we could say, okay, which one is sliding, which one is opening. And what you already can see is that the ones which has been in 45 degrees orientation with regard to the uniaxial tensor load seems to be sliding, while the 90 degrees orientation seems to be opening. Well, now we actually added more region of interest, like 19. And to click it a little bit further then, the output looks like this. So of all the grain boundaries we have, you see this distribution for the ones which has been identified with grain boundary sliding. And this is grain boundary opening. You clearly see this tendency again. Well, then finally, grain boundary migration, to be short. We have this undeformed EBSD and this postmortem EBSD. And you see this grain boundary, especially between 9 and 10 moving, but also between 8 and 9. So if you look to the strain field, you see a diffuse strain band popping up. And if you look to the incremental contributions, you see the strain band shifting down. But I think the most clear image is this one, in which we calculate the strain contribution with regard to the global strain. And then you really recognize that it is moving downwards. And finally, that this line here is almost the same as what you see there. Then the final conclusion points. So we actually now introduced novel identification methods to identify the 4 different deformation mechanisms in complex HCP microstructure, in this case zinc. So plus slip for crystallographic slip, LIDS for deformation twinning, grain boundary sliding, we use LIBS. And for grain boundary migration, we do not really have a method, but we really identify that was happening. So we underfield the deformation mechanics, and this really opens the world for more statistical analysis, but also look to really the interactions of the different deformation mechanics. And the codes will be or are available at GitHub. So yeah, you can use them. And this brings me to really my final slide. Thank you.